My name is George Crawford-Eng, and today I'm going to be presenting Lab 5, Magnetic Braking with Faraday. So the purpose of this lab will first be to collect observational data of a magnet falling through a conductive tube of aluminum foil, and then from there we will model the magnetic tube interaction computationally, and finally we will compare the computational predictions with the actual observed data. In this lab, we will discuss current and magnetic force in relation to Faraday's law. And then a preview of the results, we use GlowScript to predict the fall time of the magnet to be 1.211 seconds, and then we experimentally determined the actual time to be about 1.56 seconds. So current describes a bunch of mobile charges, usually electrons, moving through a conductor. In the diagram, you can see that the conventional current and the electron current are in opposite directions. And then the magnetic force describes how particles in a magnetic field will experience an acceleration that's dependent on the size and magnitude of their charge. And so here you can see a magnetic force generated by a wire acting on a proton. We will discuss Faraday's law, and Faraday's law relates time-varying magnetic fields to the Curly electric field, whose path integral around a closed path is not zero, but provides an EMF that can drive a current. And so in the diagram, you can see a bar magnet falling through towards a wire hoop, and in turn, it induces another magnetic field. We assume there are no non-conservative forces acting on the magnet as it falls from the tube. Additionally, we assume the roll of aluminum foil is perfectly uniform and regular, and that the bar magnet is far enough for the magnetic dipole approximation to hold. Therefore, using these assumptions in our code, we will model the roll of aluminum foil as a solenoid using the magnetic field formula there. And then we'll also represent the magnetic field of the dipole using the formula listed below. Here's the experiment setup. You can see that the system is made of the aluminum foil roll as well as the bar magnet falling through it, and the surroundings are everything else. So the reason we can't use a ferrous tube is that iron has a much higher resistivity than aluminum, so the induced current and therefore the magnetic force on the bar magnet in the ferrous tube will be much weaker. So the slowing effect of the falling through the tube will be much less noticeable in a ferrous tube. Okay, so in our experiment, we were able to measure the length to be 0.03 meters, the width to be 0.06 meters, the inner radius to be 0.026 meters, and the outer radius to be 0.031 meters. Additionally, we measured the magnetic mass to be 0.025 kilograms, and then below I have listed the 5 time trials we did of the magnet falling through the aluminum roll. And then we calculated an average time to be about 1.56 seconds. Okay, so we were able to observe that the magnet began to slow as it entered the tube, and it would continually brake until it was nearly moving at a constant velocity downwards. And we noticed that the time it took for the magnet to fall through the tube was much slower than it took the magnet to fall through free space the same distance. So moving on to GlowScript, you can see that we initialized the digital model of the aluminum foil roll using the dimensions we calculated earlier. And similarly, we will enter the mass and magnetic dipole we measured for the bar magnet as well. Similarly, we also do this with the magnet as well. And then from there, we can calculate the magnetic field to the bar magnet using the dipole B function, which I copied from my lab 3, and we use the formula below. And then we also calculate the induced EMF through a single ring using the calculate dflux dt analytic function using the change in flux formula listed below. From there, we can determine the weight acting on the bar magnet by multiplying its mass times g in the negative y-hat direction. And then we can also find the induced magnetic force using the functions that we programmed earlier. And then finally, we can get the net force acting on the bar magnet by adding these two forces together. So when we run this program, we can see from the output graph that the magnitude of the acceleration is very steep initially, but as the bar magnet enters the tube, the induced magnetic field generates a force in the vertical direction opposite to the weight. So the net force acting on the bar magnet becomes zero, and thus so does the acceleration. And using GlowScript, we were able to estimate a time of 1.211 seconds, as I mentioned earlier. So obviously there's some discrepancies between the experimentally determined value and the estimated value, and this may be due to the perspective of the camera that we recorded the magnet falling through the tube with, which made it difficult to actually tell when the bar magnet entered and exited the tube. Additionally, we did not account for the bar magnet rubbing against the walls of the roll of aluminum foil, which may have caused additional friction. And the tools we used to measure the dimensions of the bar magnet and aluminum foil roll were not very precise. We know that current is inversely proportional to resistivity according to Ohm's law. Likewise, the magnitude of the magnetic field and subsequent magnetic force on the bar magnet are proportional to the current. Therefore, minimizing the resistivity would maximize the magnetic force and would drastically slow the bar magnet's descent. If we cut holes in the tube, then there would be large discrepancies in the result between the computational model and the real-life tube, since the additional holes would make the magnetic field generated by the tube less regular. Likewise, there would be smaller change in flux, since there would be less closed surfaces, and therefore the induced magnetic force would be weaker and the bar magnet would fall faster.